Hello, guys. So we're going to start proving some theorems for series. So I'm going to recall this theorem. We haven't proved it, but I'm not going to prove it because I'm going to probably leave it for a presentation. So the theorem says a monotone sequence. What is a monotone sequence? A monotone sequence can be increasing like this one or decreasing. What does it mean monotone sequence? Increasing monotone sequence is like A1 is less or equal than A2, less or equal than A3, less or equal than A4, less or equal than A5, less or equal than. And what is decreasing monotone sequence? A1 is bigger or equal than A2, bigger or equal than A3, and so on. Okay. So it's saying that if this sequence, monotone sequence is convergent, then it must be bounded. And it makes sense because since the sequence is increasing, right, and is convergent, so at some point the distance between these guys has to be small, otherwise they will not be bounded, right? So since they are bounded for this m, this sequence, kind of the idea is that it's gonna be a Cauchy sequence. Okay, so that's why it has to be convergent. And analogously for the decreasing. So how the proof goes, the limit of the sequence is of the monotone increasing sequence is gonna be the sub, and the limit of the decreasing monotone sequence is gonna be the inf. Okay. Okay, so that's important proposition or theorem. So I'm going to introduce probably the most useful theorem for series. Okay. And also think is acknowledged to Cauchy. So it says, so this theorem is going to be very important to prove all the test integrations. So it says the infinite series sum and like that. N equals 1 to infinity. I don't know, I'm using my hand somehow. It's because it's connected. Increase this. So the sum n equals 1 to infinity of an converges if and only if for each epsilon bigger than 0 there is n such that if small n is bigger or equal than capital N and p is positive, then the tail, like a small tail, is less than epsilon. So it looks a little bit like Cauchy, right? And you can see something there. So let's see. Easy if and leave. So we have to make two proofs. right? I think the easier one is in this direction. If the infinite series converges, then for each epsilon there is n such that if n bigger equal than n and p is positive, then this is less than epsilon. So yeah, I think we can prove that. So the infinite series converges. So what does it mean? It means the limit of Sn of n goes to infinity is equals to an L on Sn equals the sum of k equals 1 to n of ak, right? So is this is a sequence, right? Sn is the sequence of the partial sums, but it's convergent. Therefore, Sn is a Cauchy sequence. Okay, we have proved that every convergent sequence is a Cauchy sequence. So the partial sums is a Cauchy sequence. That means so we're going to choose this section. So given epsilon bigger than 0, there exists capital N such that for n bigger or equal than n, Sn minus Sn is less than epsilon. Okay. So notice that I know this definition. I'm not reading the book. I'm doing my definitions by memory. So you need to know your definitions by memory. Otherwise, it's very difficult to make anything. Okay. But what I need is that this sum is less than epsilon. So therefore, if we choose, so here you can stop your video and tell me, I'm gonna choose, I can choose m equals to something such that the difference of Sn minus Sm equals what I want, that is An plus Am plus 1 plus Am plus P less than epsilon. Well, this, I know this guy is less than epsilon, so the other one is going to be less than epsilon as I wanted. Okay, so tell me what is M? So I'm going to say it. So N must be M plus P, right? Because Sn is A1 plus A2 until N minus M, but N goes to N plus P, so A1 plus A2 plus AN plus A plus 1 until N plus P. So, well, actually, it should be the other way around, huh? It should be like Sn minus Sn. Sn minus Sn. So that way, this one is plus and this is minus. So that way, this cancels with this one, this cancels with this one, this cancels with this one. So that way I get Sn minus, well, I can put it like this, right? Sn plus p minus Sn will be less than epsilon, as I wanted, right? Because I wanted to prove that this tail is less than epsilon. And look at this is the tail, and it's less than epsilon, as I wanted. Okay, so that direction. Now the other direction is if this tail is less than epsilon, then the series converges. This tail is true for any p. Okay, so let me think about it. So you also think about it, okay? Yeah, okay. So I think, as I said, it looks pretty much like Cauchy, right? So we're gonna go the other direction. So it's saying that for if it you need to notice that it doesn't say that for any p, but it's really any p because it's saying and p be positive. So this is true for any p. Okay, so you can say, let's show that Sn is a Cauchy sequence and therefore is convergent. Okay, so let n m two arbitrary positive numbers and without loss of generality you can assume m is bigger or equal than n, right? Let n be equal to two arbitrary positive numbers. So we can find p such that n plus p equals m, right? And by hypothesis, an plus an plus p is less than epsilon. Okay, that's our hypothesis because we're going in the other direction. So we're assuming this is true, right? But this is what? This is equals to Sn plus p minus Sn. But we already know that we call n plus p Sm, right? So this is Sn minus Sn. Therefore, oh, okay, so but we have to follow the hypothesis. So there exists n such that if n and is bigger or equal than n, so we need to say that it's a Cauchy sequence and therefore it's convergent. And therefore it's convergent. Let n let n and m be bigger or equal than n. So sorry, I have to fix this a little bit. Okay, let's put the n, the capital N at the end. Let n m and let's say between parentheses n is less or equal than m. without loss of generality. You can say here, without loss of generality. Okay. Two positive numbers, we can pay. And by hypothesis, there exists n you know, for hypothesis. Whoa, what did I go here? What my hypothesis? Given epsilon, this is very important. I cannot switch things around. First is the epsilon given. Okay, given epsilon positive, there exists n, capital N, such that if n and m are bigger or equal than n, then this happens. So therefore, Sn is a Cauchy sequence. And we have proved that a Cauchy sequence is convergent. Therefore, in the real numbers, Sn is convergent. Okay? So this is, like proof on the way. So let me read the proof of the book in case I need to add something to go. I think it's slightly different, but I think it's good. So we're assuming that for any epsilon, there is a capital N such that if n is bigger than n and p is positive, that any tail after that capital N is less than epsilon, right? And so we're gonna say, let's show that S with n is a Cauchy sequence and therefore is convergent. That's what we're gonna do. So we assume two positive numbers n and m, and we choose then n less than or equal than m without loss of generality. Two arbitrary positive numbers. We can find p such that n plus p equals m. Yeah, because they are positive numbers, so I can find p. And by hypothesis, given epsilon positive, there exists capital N, such that if n and m are bigger than the capital N, then this is true. This is by hypothesis. But I can rewrite it like this, right? But turns out this is my m, my given m. So that is indeed a Cauchy sequence, and because they're real numbers, is convergent. Okay, I think it's pretty much the same proof. Okay, so we're gonna prove this corollary, and then after this we're gonna prove the root test theorem. And I think I can assign a few of these test theorems proofs as an assignment. And I mean like part of the test or presentations, because then we need to move to the new topic that is continuity and basically continuity. I think we're gonna do, but we're gonna do it in topological spaces. Okay, so continuity has a lot of possibilities to do it. And then this is a good opportunity to introduce you to topology, open open sets, cloud sets, compact sets. That's something that people love to talk about in mathematics. So this is the corollary. So try to prove it using this theorem that we just proved. So if the sum converges, then this sequence converges to zero. Um, so you have, so we need to prove we need to prove that given epsilon positive, there exists n of natural numbers such that um, an minus 0, that is an, is less than epsilon, right? That's what it means. So, I can, and here on my previous theorem, that is that p can be bigger or equal to 0. That means p can be 0. So by previous theorem, if I choose p equals to 0, I have Sn minus uh, well, I guess I can choose no p equals to 0, p equals plus 1, equals 1, right? You can, it's not a problem to do it, but by previous theorem, if I choose p equals 1, you have Sn minus s plus 1, right? Now what is this? This is a1 plus a2 plus a3 until an, right? Minus Sn plus 1, a1 plus a2 plus a3 until an plus 1. So this cancel, this cancel, this cancel. So you get an plus 1. And this is less than epsilon, no? So we can, you see, we can change it slightly. Because by hypothesis here, it says for epsilon, there is n such that if n is bigger or equal than n and p is positive, then this happens, right? So it's just a number, right? It doesn't really matter. So this m am plus this is meaning epsilon is bigger than a plus 1 for n bigger or equal than n. So this is the same sequence, right? So this sequence or this sequence is the same thing, okay? So they will converge to the same point, right? I mean, like we could move it. I could choose here Sn minus 1 minus Sn, and then you'll get the An. So you could do it either way, you know? So it depends on your style. I mean, I don't think I need to change it. It's the same thing, right? So I'm not gonna, whatever this converges, the An is gonna be converged too. Okay, so I choose P equals 1. Oh, the book choose P equals 0. So the book choose P equals 0. Oh, yeah. Because I'm thinking this way, but yeah, the book is saying apply directly here. So forget about the subtraction of sums. And so if P equals 0, An is less than epsilon. Yeah, but it's no need to complicate it. Yeah, sorry, I was doing it more complicated, but it's okay. It's because I know the proof, thus I'm doing that extra step. But yeah, because this is converging, if I make P equals 0, N is less than epsilon. That happens a lot, like you do a proof today one way and tomorrow you'll totally do it a different proof. But it's kind of the same thing, so I'm not gonna change it. I leave it there so you try to see that is indeed this is the same proof, like no problem. Okay, so let me stop here to see what I prove next. Okay, so we're gonna prove this one. Theorem. Suppose on n equals 1 to infinity of n, it's absolutely convergent. Then the sum of n is convergent. The sum of n is absolutely convergent, the sum of n equals 1 to infinity n is convergent. Okay? So proof. So what we want? What do we know? We know that the sum of an is absolutely convergent. So we know that this sum is less than infinity. That's what it means to be absolutely convergent. By the theorem we just proved, right? This one over here. If there is a series that is convergent, then for each epsilon there is n such that if n is positive, is bigger than equal to 10 and p is bigger, then this happens, right? So given epsilon positive, and there is n such that an plus n plus 1. Oh, there is n such that for n bigger equal than n and p positive, then this is less than epsilon, right? Oh, but for this term, so that means I need absolute values. Okay. So turns out that this whole absolute value of positive numbers is just the same, right? So this is equals to an plus an plus 1 n plus 1 plus n plus 2 plus n plus p. So this is equals to this. Because the absolute value of absolute values is just the same. So this is less than epsilon. But this guy, by triangle inequality, is bigger or equal, right? That a1 plus, sorry, no a1, an plus an plus 1 plus an plus p. This is less or equal than this guy. Absolute value of an, absolute value of an plus p. This is less than epsilon. Okay. So we have proof that an until the sum of an until n plus p is less than epsilon. So that given an epsilon, there is an n such that if n is bigger or equal than n and p is positive, this sum is less than epsilon. By the theorem, that means if you have this, then the infinite series converges. Okay? And that's why this infinite series is convergent. Therefore, um, sum of an slash converges by theorem. Let's call it Kochi. How's the call book? Let me check the book. The book has a cool name for that statement. The book call it. What is it? So let me close it. Let me call it here on PDF. Here. So in section chapter 4. No, let me. I can share my screen here. Let me share my screen better here. So I'm looking. I'm gonna look for. This is chapter 4. Let's see. Must be the first one because it's extremely useful. Cauchy condensation test. No, that's not. This is very important too, but I'll leave it for your real analysis class to do. Let's see. Maybe here. Yeah, Cauchy criterion for convergence. This is theorem 4.11, and in the book is 224. So let's put it like that. Cauchy criterion for convergence. Over here, Cauchy criterion for convergence. Okay, so that's the first one. I think maybe one of the first one I put in this chapter 4. Test for divergence. Yeah, we did this one, no? Test for divergence. We proved that. Yeah, that's we prove. Remember, we call it test for divergence, but that we prove it. If the sum converges, then A to then converges to 0. Consequently, if an does not converge to 0, the sum diverges. Okay, so that's, it looks super simple, but um, let's say here by Cauchy criterion of convergence. So, and I'm gonna give you an example. Like I can ask you very simple questions. So, for example, by Cauchy criterion of convergence. Okay. But I was planning to give you an example. For example, this class, let's see. Yeah, well, let's put something like class 5n. Okay. So clearly we know it's not gonna be convergent, right? Because it's gonna increase. But I probably can give better examples. But you know, because an does not converge to 0, it is divergent. Maybe we can do something better. Oh yeah, let's do something like this. Like I'm gonna put 2. Oh yeah. Let's put it like this. Yeah. Okay, let's put it like this. This one is better. N plus 1 over n. This one is divergent, right? Because an, the limit of an is 1. It's not, it doesn't go to 0, so it's divergent. Okay? Good. Okay, so last one. Only you guys. I wanted to do comparison test, but maybe I'm gonna assign it as a presentation. Because it's not that basic, but it's not that. I'm gonna do the root test. Turns out the ratio test is a little bit harder than I thought. I thought the ratio test was easier than the root test. I'm gonna do the root test. We can do the ratio test maybe at the end if we have time. But for now, I'm not interested to give you really long proofs. I want you to learn to the logic through exercises and through not that long proofs. There are proofs that are long. Okay. So there are proofs that definitely you need to read the book. Oh, sorry, you guys were not looking at this. Okay, let me fix that. Okay, there. So I was showing you. Sorry, I don't know. I don't remember how much I was not sharing, but I was showing that this example is not convergent. It's divergent because this limit does not go to 0, goes to 1. And also, I call this test, oh yeah, Cauchy criterion for convergence. So I add at the end of the proof, therefore this sum is convergent by Cauchy criterion of convergence. Okay, good. Okay, let's finish. Good. Because knowing why the root test is convergent is very useful. I mean, I think we can use the root test to prove the ratio test. I had to think. Because I read the proof of the book of ratio test. Honestly, I tried to do the ratio test proof and I couldn't. I was not convinced of what I did. So when I read the book, it looks a little bit harder. I think there is an easier proof. So root test is good, easy proof. And I know we can use the root test to prove the ratio test. So maybe that would be a nice way to do it. Well, let's see. Theorem, root test. So let's see what the root test says. Suppose sum of n equals 1 to infinity n is an infinite series. It's very easy proof. You're gonna like it. Then one, if there is a real number q such that q is between 0 and 1 and a positive integer n such that the n root of an is less or equal than q for n bigger than n, then the sum of n converges absolutely. Okay. And part two says that let's just leave it like that. Let's not do this part. This is clear. Okay. So it's saying that if there is a real number q such that q is between 0 and 1 and a positive integer n such that this is true for all n bigger than n, then the sum converges absolutely. This is proof. So we know that the n root of an is less or equal than q. So then taking the power to the n on both sides, we get less or equal than qn. Okay. But now what? Remember, this q is between 0 and 1. Therefore, the sum of n equals 1 to infinity is less equal than the sum of the qn n equals 1 to infinity. Okay. But this is convergent because it's a geometric series. This is less than the infinity for being a geometric series. So if this is a geometric series and is convergent, therefore this one is absolutely convergent. Therefore, the sum of n equals 1 is convergent by the comparison theorem that we haven't proved. But some of you is going to prove. Okay, well, as a presentation. Okay, and then that's it. So we have proved the root test. So, root test is very important for PDEs. And you have already a lot of examples in your homework there. So yeah, so we can do a lot more. It's whole books of series and sequences and power series. But I think we have done a good number of proofs and examples. So we might come back later to see if we have time, but we have to move to topology now. So we're gonna do next video is not part of the exam, and we will do topology. We will start topology. We will do continuity of functions. Okay, I'm gonna stop this. How do you recording? Oh yeah, it's recording good.